Versus ground.
Also, I don't know, the other thing with like email, I don't think that.
Let's go ahead and get started.
That's all you said.
Today we're going to be talking more about momentum and collisions. And so I got a little bit of demonstration here. A little note before I get started though. So I entered in midterm grades. You guys may or may not be happy with it. And if you're unhappy, keep in mind that there's only been about 25% of the points have been gone through for the class. Because we got 2 more midterms and a final and half the homework to do. So, I mean, you can definitely bring up your grade. You have opportunity to bring up your grade a heck of a lot at this point. But it will, if you're not doing well and you keep doing that same thing or not doing it, not doing what you should be doing, it probably will not improve. That's just been what I've seen. So it's up to you kind of what you want to do if you want to start improving it dramatically. Okay? And I think the real key is to be able to do problems. If you can do problems on your own and get the right answer, you're good. If you can't do problems on your own and get the right answer, then that probably means you don't know the subject well enough. And that's the beautiful thing about physics is it doesn't lie to you. There are right and wrong answers. There's not a lot of gray area. And so it's pretty clear whether you can get the right answer or not. I got some problems posted up on Blackboard. There's some extra ones. I'll see if I can get some for momentum up there. And if you do a Google search for problems with answers, I'm sure you'll find for algebra-based physics 1, I'm sure you'll find a lot of them. And you can, and if you just go through those, you'll see whether or not you know it or not. Okay? So, all right. Let's go back and talk about momentum. Does anyone remember, what was the definition of momentum that we had? That's right. The vector P, which is momentum, is mv for a single mass. If I had a bunch of masses, P total, I would add up all the momentums of each of the individual masses. That's it. Okay? And we saw that in the absence of external forces, no external forces to a system of maybe 2 particles. So that means only if you have masses just acting on each other. So masses just exerting forces on each other. Then the total momentum is a constant. So that means that the momentum doesn't change if we just have masses interacting with each other, and that's the only forces that we have. Oh, can you guys see with this thing? Put this down here for now. And this leads us to be able to handle collisions, because during a collision, it's 2 masses acting on each other, right? They hit each other. And so before a collision and after a collision, and after a collision, the momentum is the same. So I can write that if I have two masses, m1, m2, this one's going with some speed, velocity v1, this one's going with some velocity v2, and they hit each other, then they, afterwards, maybe they're going at some other, so m1 going this way, v1 final, then m2 going this way, v2 final. This is after. Then we have to have that m1 v1 plus m2 v2. That's the momentum before the collision. That has to be equal to m1 v1 final plus m2 v2 final. And that's the momentum after the collision. And that's just a consequence of the momentum being constant if the masses just act on each other. Then we talked about two types of collisions. These are kind of special type. Most collisions don't really fall into either one of those. These, we had inelastic collision. With these, the two masses stick together and travel with the same final velocity. V1 final is equal to V2 final. That's the condition for an inelastic collision. And then we also had elastic collisions. And we haven't really talked anything hardly about these. But with these ones, not only is momentum conserved, but also the kinetic energy is the same before and after the collision, because there's no energy, there's no way for the energy to be lost during an elastic collision. So kinetic energy initially is equal to the final kinetic energy, and for a two masses hitting, it'd be like 1/2 m1 v1 squared. M2 v2 squared is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Where v1 and v2 were like over there, those were the initial velocities. And in this case, max speed. So that's basically what we did on Friday, okay? Went through all of that. And then we did a couple of examples. So now we're going to go ramp this up and do a few more examples. The first example I'd like to do is this one. So this is what we call a ballistic pendulum. You will be dealing with this in lab this week, or something very similar looking. All right, so let's just see what happens with it. So if I shoot it like that, what happened? See what happened? The ball got stuck in there, in this but during the collision, what type of collision would that be?
Inelastic.
Good. And that's because the two masses are stuck together and moving together after. So, and so with this situation here, what we have, I'll just try and draw this. The idea behind this is that you'll be able to figure out the initial speed of the ball by seeing how far the ball and the catcher move up together after the collision. So let's see if we can go through this really quickly. So ballistic pendulum. This is a classic problem for momentum. And it involves also energy too. So initially, And this I mean right before the collision. So after I fired the projectile, but before the projectiles hit the holder, I have a pendulum that's free to move. And I have the ball moving with some velocity vi in the x direction. And I'm going to leave off the vector here. It's one-dimensional velocity in this case, we'll see. And it's about to hit this, okay? This has a mass of m1, this has a mass of m2. So right after the collision, how fast is the ball catcher with this thing going? So after the collision, can you guys see down here? Probably not. After. You have the ball catcher with the ball in it. And this thing is moving with some final speed v final. Okay? So, in terms of this stuff here, let's see if we can get v final. What would that, how would you do that?
We the initial and the final setting them equal to 0.
Okay, setting them equal to 0.
I mean, setting them equal to each other. So.
Okay, good. So initial momentum. What's the initial momentum?
M1,
Yeah. M1, V1 in the x direction. Yep. That's right. M2, the velocity is 0.
Mm-hmm.
So there's no so it doesn't have any momentum. And I'll just write this is the momentum in the x direction. Finally, what would it be?
It would be,
M1 plus M2.
yeah. V final.
Final, right?
Mhm.
Because they're moving together. And these two have to be equal to each other, don't they?
Mhm.
So I would just write M1 V1 is equal to M1 plus M2 V final. And so if I wanted to get what this V initial is, or this V final in terms of this stuff, what would I do?
Divided by the mass.
Yeah, that's right. So I do M1 V1 divided by M1 plus M2 is equal to V final. You see that? Okay. Now after this thing's moving with a V final, it swings up to a certain height. The center of mass rises a little distance. It's getting hit and missed. Center of mass went from like here to here. So we'll call that a distance h. So after the collision, there's no, there's no friction up here. The work here is only done by gravity. That's because the tension force on the pendulum is perpendicular to the motion. It's not doing any work. So if the work done by gravity raises this a distance h, can we get what this V final was? So this is just after the collision. If we have work only done by gravity, what did we do? That was that kinetic energy and potential energy thing,
Yeah,
right?
P equals mgh.
Yeah. The kinetic energy, if the only work is done by gravity, the kinetic energy plus the potential energy is going to be a constant. Okay? So between this situation where it first started moving with this V final, to where this ballistic pendulum comes up to the final height, which is like up here, we can see what, you know, we can treat that as the initial and final places where the energy should be evaluated. So we should have the potential energy right after the collision plus the kinetic energy right after the collision is equal to the potential energy after it's done its swing plus the kinetic energy after it's done its swing. We call this y equals 0, or h equals 0. What would be the potential energy there? 0. What would be the potential, the kinetic energy right after the collision?
1/2 mv squared.
Which m?
M1 plus M2.
Yeah, m.
Plus m2 v final squared, right?
Yeah.
And that would be equal to, what's the kinetic energy at the end?
0.
0.
0. And the potential energy at the end?
mgh.
Which m?
Oh, m1 plus m2.
pH, okay? Good. And so I get that, and I can divide out these m1 plus m2, right? I get 1/2 v final squared is equal to gh. I can multiply both sides by 2. I can get something like that.
The the kinetic final is 0 because velocity is 0, right?
Yeah, that's right. It just came up here and came to a rest. And this thing is swings freely upwards.
Okay.
So it'll swing up, so there's no real friction going upwards.
Okay.
But it'll lock itself because there's a little ratchet
Okay.
and will come down.
No, you won't. Too.
Okay, now the idea that we want is eventually with this ballistic pendulum is you'll want to be able to solve for this speed of the bullet knowing all the masses. And you can do that, you know, we just take this and plug it into here. And then you could solve for what V1 is.
Oh, you take that and plug it over there?
Take this, plug it into here. I guess you could do that same, you could do like this, and plug this into here. It doesn't really matter.
Oh.
That's probably easier.
Yeah, that's
And solve for V1. Okay. And that would tell you what the initial speed of the bullet is. So, and that will be what you're doing in lab. So I won't go through it in more detail. Okay. We'll do an example of an elastic collision now. And that's what this thing is. I don't really know if this is going to be useful. This is called Newton's cradle, and you've probably seen these. And if I pull one of these out, what's going to happen? What's that? One on the other end will go up, same height, right? And it's you can see it's moving up basically the same height, so the kinetic energy right after the collision would be the same, right? What happens if I take out 2 of these? Huh. Pretty neat, isn't it? What happens if I take up 5 of these on this side?
I'll go 3, and then there's going to be 3, maybe. I don't know.
There's going to be 5.
See?
Oh, cool.
Yeah. So, let's see, maybe 3 is better. Starts to get a little wiggly, you know, with that. But, yeah, and the more aligned you get it, the more and less wiggly it gets, but it's kind of hard. You have to be pretty careful about it with a lot. But you see what it's doing with 5? see if we can understand that, okay? And the reason this is an elastic collision is there's no real deformation of what's colliding, so they don't stick to each other and they don't deform in any way. So there's no real good way to lose energy during the collision, and so that means that the kinetic energy, would be the same before and after. And so for an elastic collision, we have that the kinetic energy before and after is the same. Let's see for this Newton's cradle that will imply that, if I drop two balls, two other ones have to come up. So, well, let me just draw it. This is, it's not the full example because that one has more. But let's say I drop one of them so that this has an initial speed, VI, going this way when it hits these other balls, okay? So that means the momentum in that way has to be the same before and after the collision. So this is before. Maybe right before I'll draw this as be like this, okay? And then after, see if we can figure out what will happen after, and then we'd understand it. So all these have the same mass. So M, 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 M. Okay? All of them have the same mass. And kinetic energy has to be conserved for an elastic collision. Now for just a general collision, there are many ways you could conserve momentum, right? I could have a MV going down here and then have all these four move up at a quarter V. That would appear to conserve momentum, wouldn't it? So let's go, but that wouldn't conserve kinetic energy. So let's go ahead and see why that's the case. So let's just suppose that if I drop one, all four of them move, say, okay? So suppose this is, and we'll show that that can't possibly work. Suppose that that after the collision, four masses move at 1/4 V1, V initial. It's an I. Well, that would definitely conserve momentum, wouldn't it? Because my initial momentum in the x direction, let's say I draw the x direction. Let's draw the x direction backwards, going that way now. Okay? My initial momentum in the x direction is m v initial, one mass hitting the other ones. And if four masses moved at 1/4 vi, my final momentum would be m times 1/4 vi plus m times 1/4 vi 4 times. So that'd be 4m times 1/4 vi, which would be m vi, right? So clear that momentum is conserved. Let's go see that kinetic energy is nowhere near conserved, okay? And then we'll see that in order for both momentum and kinetic energy to be conserved, only one mass will have to be moving with the initial speed. So, does this make sense to what I'm doing? So, kinetic energy. So elastic collisions have the same kinetic energy before and after the collision. So what's the kinetic energy before the collision?
0?
One half
No.
MVI.
So I have
Oh,
one
yeah,
mass
yeah.
moving with a
One
speed
half.
VI, right?
Yeah, 1/2 m
1/2 m VI
I
squared.
squared.
Good. Now, if I had this situation here after, what would be the kinetic energy after the collision?
One half 4m, 1/4 vi squared.
1/2 m.
2m, 1/4 v squared.
Yeah, that's right. So 1/4 VI squared plus
Which one?
another one 4 times, so it'd be 4 of those. And that would be 2m times 1/4 VI quantity squared. What's this? 1/16 VI squared, isn't it? That's because I have to square that 1/4, right? It's 1/16. So this would be 1/8 m VI squared. That's not equal to kinetic energy initial, so this wouldn't work for an elastic collision. In fact, any combination I can find where I have more than one mass moving will work to try to conserve kinetic energy. You can give it a try. Say if say instead of 4 I had 2 masses moving at 1/2 of the initial velocity, or some combination like that. You know, if I had that case, then I'd have 2 here and 1/2 here, 1/2 here, and then I'd have a 1/4 VI squared instead of a 1/8, and that's clearly not the 1/2 MIV squared, right? MVI squared. So any combination I have where I have more than one mass moving after the collision that conserves momentum, kinetic energy is not going to be conserved. But you can see at the end that if I get rid of this and force this to be moving with VI at the end, that has both momentum being conserved and kinetic energy being conserved. Make sense? So that's the reason why, you know, if I drop one mass, one comes up. If I drop 2 masses, the same mass has to come up to conserve kinetic energy with the same speed. And, you know, that's why that thing's working the way it is. Does that make sense?
So what's up when you do the 5
When I do 5, well, that's 5 masses. 5
against
M
3?
coming down, and 5
Oh,
could come
okay.
up at the end. And so it looks like, make sense? Good. Let's do an example. Well, okay, I'm gonna do a pool example here. So the problem with, there's always some trickiness when we have to deal with a general problem of collisions. And I'll give you one as maybe a project thing right at the end of class today, and see if you can get it done by Tuesday. There's always some problem that becomes kind of complicated. But there's some general principles that seem to work when we're dealing with elastic collisions. Let's do a typical example. Let's say I have 2 of the same masses, and only one of the masses is moving to begin with. Okay, this is for an elastic collision. So this is an example of a pool ball. So this is the initial situation. Afterwards, I have M here. I'm going to call this V1 and V2. So M, V initial, and then 1. So this V1 afterwards, V2 afterwards, okay? And if I'm doing with 2 dimensions, unfortunately I have to deal with vectors. If it's a perfectly head-on collision, perfectly head-on, this will move same speed after the collision as the original ball was going before the collision. That conserves kinetic energy and momentum. If it's not perfectly head-on, so that the collision is sort of not at the center of the ball, but off a little bit, it is no longer head-on, and this object won't move straight forward, and you'll get a situation kind of like this. So there's in practice, we can actually figure out what V1 and V2 are for any given VI here. And I might leave that as some exercises for you at the end of the day. I'll give you some numbers. But I want to do one simple little proof. If I were to draw a line along this V2 and a line along this V1, turns out the dead angle is a 90-degree angle. So let's go see let's go see why that's the case. So when you're playing pool, so my sister's a pool shark actually, and she likes playing a game called Carom. I don't know if any of you ever play that much, but and there's a bunch of examples of this. That's where you hit the object ball off the cue ball, and then the really distinguishing feature of good pool players is that they always set up their next shots pretty easily. And they do that by knowing exactly where their cue ball is going to go after their first shot. And knowing that they diverge at right angles and with no spins is a kind of a key thing. By the way, if you put top spin on, the angle gets smaller. If you put back spin on, the angle gets wider. English, well, a lot of good pool players don't even deal with English. So, 9-ball players do, but anyway. Let's go see that this diverges at the right angle. So, let's look at the momentum before and after the collision. So I have before. The momentum is M, VI, right? That's a little I. MV, that's the momentum before the collision. What's the momentum after the collision? It's MV1 plus MV2, right? And so these things have to be equal. So I would get that MVI is equal to MV1 plus MV2. I can divide through by M's, and I get that VI is equal to V1 plus V2. Let's kind of see what this means. You can kind of, this is VI, sorry. A little dot there for the I. So that means that if I added up these two vectors graphically, that they should equal this vector, right? That's what we're saying. So if I add up vectors, what does it look like graphically? I put the tail of one on the head of the other, right?
Mm-hmm.
So if I have V1 like this, and V2 like this, you know, this would be VI. Okay? That's what it means to add up vector V1 plus V2 is equal to VI. This is what it means graphically. Right? Now let's take a look at the kinetic energy conservation equation. So, assuming this is an elastic collision, which it is, there's no good way to lose kinetic energy. The balls aren't deformed after the collision. What's the kinetic energy before and what's the kinetic energy afterwards? So what's the kinetic energy before?
1/2
V1 squared? This
Initial.
V initial squared.
Mm-hmm.
Okay. This is the magnitude of that V initial velocity vector, the length of it, you could say. And what's the kinetic energy afterwards?
1/2 and finals. No. Yeah.
What are the final velocities?
V1 squared, V1,
Squared plus?
Plus 1/2 and V2 squared.
Okay. Let's divide through by a 1/2 m. I squared is equal to V1 squared plus V2 squared. See that? Okay. Now, this thing kind of gives us a relation between the lengths of these vectors that I drew here, right? In fact, that's the Pythagorean theorem for this triangle. Now, Pythagorean theorem only holds in the case of right triangles. That means this is a right triangle, and that those two velocity vectors are at right angles with respect to each other. And so we prove that this and this diverge at right angles. All right. Okay, now here's an exercise. You spend the next 10 minutes doing this if you can. I hope you guys can do it. And if you don't finish it in the class time, I'll walk around. If you don't finish it in the class time, we'll do it at the beginning. We'll cover it at the beginning of the day on tomorrow. But here's the idea. So let's say I have a V initial here. All these have the same masses. V initial is 5 meters per second. That's a pretty hard shot. Pretty cool. And then hitting off center on some other ball with the same amp. So this is initially. Okay, after the collision, the two balls, I'm going to call this 1 and 2, diverge. One is moving up at an angle of 15 degrees above its original position. And then the other one is moving down. So this is 1 and 2. Then you go ahead and figure out what those final speeds are, knowing that this is an elastic collision. So find V1 vector and V2 vector. Alright, so you feel free to work with the people next to you and apply the momentum conservation and kinetic energy conservation. I told you that, okay, so this thing, these two have the same masses. This thing's going at 5 meters per second. It's the second ball, a little offset. So the first ball then moves upwards at 15 degrees above its initial trajectory. Can you figure out both the speeds? So what you're going to do is you're just going to write momentum before is equal to momentum after. Start writing out those velocity vectors in terms of just angles you draw. And then kinetic energy before will be kinetic energy after. Okay. To make it interesting, maybe if people turn in correct answers, nice box, correct answers, tomorrow morning, I might give them 5 extra credit points. Okay. On a test.
Oh, look at that.
Okay.